Section: Introduction. In this section, we introduce the concept of autonomous digital agents that can assist us in various tasks, leveraging the advanced capabilities of large language models, LLMs. These agents, powered by LLMs, have the potential to revolutionize how we interact with technology, making our daily routines more efficient and expanding the possibilities of machine-assisted productivity. We identify several challenges that need to be addressed to enable these agents to navigate the web effectively. These challenges include the absence of a unified action space for tasks across different websites, the complexity of web pages making it difficult for LLMs to understand and act correctly, and the lack of high-quality training data for training robust LLM-based web agents. To tackle these challenges, we present a AutoWebGLM, a web page browsing agent based on the ChatGLM 3-6b model. Unlike its predecessor, WebGLM, which focuses on question answering, AutoWebGLM is designed to autonomously perform complex tasks on real web browsers. We propose efficient data strategies to quickly build a reliable training dataset and use supervised and reinforcement learning to train AutoWebGLM for general web page browsing tasks. Furthermore, we introduce rejection sampling fine-tuning, RFT, for lifelong learning in specific web environments, allowing the agent to specialize in a particular domain. By developing a Chrome extension based on AutoWebGLM, we demonstrate its ability to reason and perform tasks accurately on various websites, making it practical for real-world applications. Additionally, we create a bilingual, English and Chinese, web page browsing evaluation dataset to account for stylistic variations in websites from different regions. Through experiments, we show that AutoWebGLM achieves performance comparable to state-of-the-art LLM-based agents and is highly effective for real-world web tasks. In summary, our contributions in this paper include designing and developing the AutoWebGLM agent for efficient web browsing, constructing a real web page browsing dataset, and demonstrating the agent's practical usability for a wide range of tasks. Section Summary. In this section, we introduce a AutoWebGLM, a web page browsing agent based on the ChatGLM 3-6b model, designed to autonomously navigate and operate on real web browsers like humans. We address challenges such as the lack of a unified action space, web page simplification methods, and high-quality training trajectories for LLM-based web agents. By leveraging supervised and reinforcement learning methods, we train AutoWebGLM to excel in general web page browsing tasks and employ rejection sampling fine-tuning for lifelong learning in specific web environments, making it proficient in various websites and tasks. Section: Observation Space. In this section, we propose using a unified observation space to improve our model's understanding and performance level. This observation space should contain key information similar to what a browser's interface offers, maximizing the agent's capabilities. We have identified 4 crucial indicators for web browsing tasks: task description, simplified HTML, current location, and past operation records. The HTML provides structural and content details about the page. The current location helps the model know where it is on the web page, and past operations give historical context for more consistent future actions. By including these elements in the observation space, we aim to create a stronger and more practical model that can handle the complexity of web browsing tasks effectively. When dealing with HTML web pages, which can be vast and intricate, it is essential to simplify them before inputting them into the model. This simplification process aims to extract necessary information while removing unnecessary elements that could confuse the model. The basic structure and significant content of the HTML must be preserved to enable the model to understand and use this information for efficient web browsing. We have an algorithm in the appendix that can convert a tree of elements into a concise representation, making the HTML format more understandable for the model. Based on our observations, agents perform better when provided with window position and page size information. Knowing the page scroll position helps understand the visible content, while page height gives a sense of the entire page's scale, providing spatial context for the model. Explicitly informing the agent of past operations helps prevent it from repeating ineffective actions, improving its ability to adapt to the complexities of web browsing tasks. As we focus on building a language model-based web browsing agent, we design the action space based on operational possibilities. By summarizing real task experiences, we define a comprehensive action space as function calls for the language model to navigate the web effectively. To address the challenges of creating a training dataset due to the scarcity of high-quality web browsing data, we suggest a hybrid human-AI data construction method to overcome these obstacles. Efficiently understanding and manipulating web pages are crucial challenges in model development for web browsing tasks. Our method for web recognition and simple task operation construction aims to train models to recognize web page structures and perform basic operations accurately. Web recognition involves understanding HTML formats, identifying web elements, and their functions. We collect URLs from various websites, simplify the HTML structure, and design tasks to aid model recognition. For simple task operations, we collect websites, split operations, and adjust data size based on operation frequency. We construct the dataset using rules and model assistance to ensure task accuracy and richness. Section Summary. In this section, we propose utilizing a unified observation space to enhance our model's web page comprehension and operational capabilities by incorporating critical indicators like task description, simplified HTML, current location, and past operation records. By simplifying HTML structures, providing current position information, and informing the agent of past actions explicitly, we aim to create a more resilient and practical model for handling the complexities of web browsing tasks effectively. Our approach focuses on constructing a language model-based web browsing agent with a complete and self-consistent action space, overcoming challenges in data preparation through a hybrid human-AI data construction method to train models for accurate web page recognition and simple task operations. Section: Complex Task Operation Construction. In this section, we developed a dataset for complex web tasks to help our model plan and reason during web browsing. Each sample in the dataset includes a real-world complex web browsing task, the sequence of operations needed to complete the task, and the intent behind each step. We created 50 complex tasks for each website using a prompting technique and manually selected about 20 feasible tasks. Due to the complexity of the tasks, even advanced language models struggle to complete them accurately. Therefore, we used manual annotations to track web task executions through a browser plugin that records actions during website tasks. Chain of thought reasoning has been shown to enhance task understanding and model performance significantly. However, relying on human annotators to document their intent and reasoning during web browsing is inefficient. To improve this process, we used GPT-4 as the operational intent predictor. Our initial step-by-step creation approach resulted in weak operational links and high API costs. To overcome this, we implemented a global thought chain prompting method where all operations and critical HTML segments are inputted into a trace, and GPT-4 is prompted to output intentions for each step. This method enhances the accuracy and cohesion of each step, leading to highly relevant and consistent thought chains. After constructing the data, we combined it with training sets from Mind2Web and MiniWab++ to create our final training dataset. We divided the complex task operation dataset into two splits for evaluation, in-domain and out-of-domain. The in-domain dataset consists of training data from the same website to assess the model's performance under familiar conditions. In contrast, the out-of-domain dataset includes data from websites not included in our training set to evaluate the model's generalizability and adaptability to new environments. We selected 50 browsing traces for each split as test data, which were carefully reviewed and filtered for a more reliable evaluation benchmark. Following the methodology in Mind2Web, we thoroughly evaluated each step of the operation to assess the model's accuracy. Our model training process involved 3 steps illustrated in the figure. The first step is curriculum learning, where we utilized supervised fine-tuning, SFT, with data from the previous section to enhance the model's understanding of web pages and its ability to perform operations. We employed curriculum learning to gradually advance the model from simple to complex tasks, mimicking the human learning process. This approach has been shown to significantly improve model capabilities. In the initial stage, we trained the model to comprehend web page structures and execute basic operations based on user instructions. In the subsequent stage, we trained the model to decompose tasks into subtasks and execute steps based on prior operations and the current web page. After the initial training, our model, M_text SFT, gained the ability to complete web browsing tasks and execute operations independently. The second step involved reinforcement learning to address issues such as hallucinations during inference. We proposed a self-sampling reinforcement learning method to mitigate these problems by using M_text SFT for multiple samplings on task samples. We constructed contrastive data with positive and negative pairs to help the model learn from its mistakes and improve its capabilities. Section Summary. In this section, we developed a dataset for complex web tasks to enable our model to plan and reason in web browsing scenarios. By leveraging manual annotations and a global thought chain prompting method with GPT-4, we improved the accuracy and cohesion of each step, forming highly relevant thought chains. We then trained our model through supervised fine-tuning and reinforcement learning steps to enhance its comprehension of web pages, ability to execute operations, and mitigate operative illusions. Section. Step 3. Rejection Sampling Fine-Tuning. In this section, we focus on rejection sampling fine-tuning, RFT, to improve our model's performance in specific web page environments. RFT allows us to train our model more effectively by sampling extensively from an existing model and selecting the correct paths in cases where there are no clear paths using reward signals. These reward signals can come from the environment itself or from predefined reward models. Due to the constraints of network policies in real web page environments, we conduct our experiments in sandbox environments provided by MiniWAB++ and Web Arena. In MiniWAB++, we use the query generator to create multiple user queries for each task, adjusting the number of queries based on task difficulty. We then use M_text DPO to solve these queries. If a trace successfully completes the task in the MiniWAB++ environment, we consider it a positive trace. In Web Arena, we manually create distinct user queries based on Web Arena's templates to avoid overlap with the test set. We apply M_text DPO to perform 64 sampling attempts for each sample. If our model completes the task at least once based on manually defined rules, we consider it a successful trace. By following these methods, we create two separate successful datasets from MiniWAB++ and Web Arena, which we use to fine-tune AutoWebGLM for these tasks. We then conduct experiments to evaluate AutoWebGLM's performance on a bilingual benchmark called AutoWebBench, comparing it with publicly available agents. We also test AutoWebGLM on various benchmarks like Mine2Web, MiniWAB++, and Web Arena to assess its performance against different baselines across tasks involving navigation on English and Chinese websites. To further analyze the impact of different data and training strategies on model performance enhancement, we carry out a detailed ablation study. By examining the effects of training with different datasets and strategies, we observe that incorporating complex task data significantly improves model performance by better aligning with real-world scenarios. Additionally, training with a combination of simple and complex task datasets leads to substantial performance enhancements, while training solely with complex task datasets may result in basic operational errors that can be mitigated by including simple task datasets in the training process. Comparing different training strategies, we find that DPO training helps the model learn from its mistakes, while RFT allows the model to improve across different domains through Bootstrap enhancement. Section Summary. In this section, We optimize for web page environments in specific domains through rejection sampling fine-tuning, RFT. RFT allows us to target training by extensively sampling from an existing model, selecting accurate trajectories in instances lacking them using reward signals from the environment or pre-designed models. Our experiments in Mini-WAB++ and Web Arena environments involve generating user queries, solving tasks with M_text DPO, and constructing successful datasets for AutoWebGLM's individual fine-tuning. Section: Case Study and Error Analysis. In this section, we assess the effectiveness of our model through various case studies involving different web-based tasks like everyday use, leisure, relaxation, and academic research. Our system performs well in most scenarios, as detailed in the appendix. However, we do encounter errors during task execution, including hallucinations, poor graphical recognition, misinterpretation of task context, and pop-up interruptions. These errors, though infrequent, are crucial for improving our system's capabilities. When it comes to constructing a comprehensive web browsing agent, it involves different modules like a language model for decision-making and an HTML parser for observing the environment. It's also important to establish suitable evaluation criteria for effective web browsing. We will now discuss related works in these areas. Large language models, LLMs, such as GPT-4 and others have excelled in various natural language processing tasks. However, due to cost considerations, smaller models like Llama 2-7b and ChatGLM 3-6b are preferred for their comparable performance at lower costs. For evaluating web browsing, benchmarks like Mini-WAB++, Mind2Web, and Web Arena offer different metrics to assess model capabilities in interacting with web page components and completing tasks efficiently. Previous works like WebGPT and WebGLM focused on question-answering tasks using Internet resources. Recent works like MindAct and WebAgent concentrate on executing complex operations or interactive tasks. These newer approaches show promising results in filtering web page elements, generating code to control web pages, and enhancing web browsing performance. Prompt-based data construction methods have gained popularity recently, leveraging language models to generate synthetic data for training. For instance, Evil Instruct demonstrates the effectiveness of using LLMs to create diverse and complex instructions for various tasks. This approach shows potential in generating data for tasks the model has not been explicitly trained on, offering a versatile and efficient way of data generation across different domains.